Morning, guys. Morning, Azra. Morning, Downey. Hey, Hayden. Hey, Hike. Hi, Charlie. So, issues with ELA. I think you guys got to be a little patient. I wouldn't. I wouldn't freak out too much. It'll be put up when it gets put up. I'll let Miss Kildoff know right now, actually. Yeah, she's in a meeting. She'll be done around 11, but I just sent her a message, just letting her know. But again, just like in ELA, you got to be a little patient. Miss Kildoff is trying to run, the ELA classroom at the same time. She's trying to take care of her own classroom and students. So just be a little patient. There'll be a substitute at some point the next couple days, and you'll just pick up where you left off. All right. So today in science, the agenda, we have a second DNA question. You'll have one more tomorrow, so you have 3 this week with your DNAC 23 on Thursday, because you guys aren't going to be in school on Friday. Teachers are planning. You guys are finishing what you need to finish or just taking the day off. So we have one more to do after today's second one. Then I'm going to review again the rubric and the objectives for a tour of the solar system. I just want to be real clear because I'm not there with you, being able to understand what I'm looking for and how the process is going to go. Right now, it's pretty straightforward. There is a research table, and you're filling out the different categories for your planet. All right, based on accurate, reliable sources. So that stuff's pretty straightforward. What's going to get a little more confusing is how do I make these into slides, and then how do I use Screencastify to record my voice over my slides as I kind of like present them. I don't need your face. I don't need you projecting it and recording yourself. Just recording the voice as you do your slides, kind of like how I show you a little bit, or how Mr. Howman makes his videos using that extension in Chrome. All right. And if it's way beyond what you want to do, you're not comfortable with it, you can just write up a small paragraph about how you would explain your slides, what's the importance of your planet in terms of scientific study. All right. We'll talk about that definition of a planet again later too. Continue the research of your planet of choice. Do another like 2 or 3 boxes in that table. So maybe half the table is done, is researched. All right. My goal is to have a lot of your research done this week, over the weekend, and then you come back on next Monday and we're ready to work on the slides. Talk about how to record yourself. All right. And then probably the due date for this, again, pushed. It's either Tuesday, Wednesday. We'll start to know more firm deadlines later on in the week. All right. So your second DNA question, hopefully you're already answering it as you're listening. I'll go over it in a little bit. The dwarf planet Ceres was once thought of as an asteroid, was actually once thought of as a planet, then an asteroid, and is now considered a dwarf planet because of the definition of a planet, has a mass of, let's see, I did this earlier. That's 1,000, that's million, that's billion, trillion. Wait, did I do it right? I think I missed a set of zeros. Thousands, millions, billions, trillions, quadrillions, 900 quintillion kilograms. So the dwarf planet Ceres Still much smaller than the Earth. If you watched my video on what would happen if the moon blew up, we talked about using Ceres' mass, carving up the entire dwarf planet and putting it on the Earth. You would need 30 of them. Oh, no, I can't remember the exact number. No, like in the thousands, 1,200 Cereses carved up and placed on the Earth to create a Roche limit where you would shred the moon apart by gravity. Ceres has 900 quintillion kilograms. Write its mass in scientific notation. Don't remember what that is? Go back to DNA number 1. How do you write something that large of number in scientific notation? Hint, we use powers of 10, right? So some number times 10 to what power? The dwarf planet Pluto, which is located in the newer region that we've kind of defined in the solar system, the Kuiper Belt, past the orbit of the planet Neptune, has a diameter of 2.3 times 10 to the third kilometers. Take that number and now, in scientific notation, make it into a standard format, into standard notation. So write it out. So the first one, you are converting this number into scientific notation from standard appearance. And this next one, you're taking this number and you're putting it into standard notation instead of scientific notation. Can you go back and forth? Talk to Miss Grant a little bit about scientific notation. And you guys will be going over more of it too in math next week, which is pretty cool. So, like, once again, math and science helping each other out, just like when we did slope. It's almost like math is the language of science. Would it be 9 times 10 to the 20? Is there 20 zeros like you said, Jake? You got to move that decimal place over? Sounds right. We'll check it in a couple minutes. Oh, I didn't see Sam. Hi, Sam. So we got an update on your reading. She doesn't have access to the book, like you guys were saying, but she did record herself reading it, so she's going to post that after her meeting. So that's going to be probably a little around after 11 o'clock. All right? So those of you who are worried about ELA, again, relax. Big event happening for Miss Mikett, and it happened sooner than it was expected, so things are getting put together quickly, but still takes time. The reading will be a recording of Miss Kildoff reading it. Will be posted after 11 o'clock. All right? Hayden, you forgot how to do this? Well, hint, powers of 10. You can multiply something by 10 to add a 0. That's what scientific notation is. So you can write a small number times 10 a lot of the time, and you'll get an equivalent number. Speaking Hayden, I did a lot of reading yesterday. I looked at web pages, University of Illinois. I looked at different articles, Scientific American, and I found that there was no answer on why the speed limit of light is 300,000 kilometers a second. There was a lot of information about light being constant and being proven that it's constant in a vacuum. There was a lot of special and general relativity, which means gravity playing a role in bending space that we're going to talk about later on in the unit. Gravity bending space and therefore bending light, and that taking more time when you bend light to get from one point to another. So you could actually have light still be the same speed, but actually take more time to get somewhere, which kind of makes it appear slower. So there was a light stays constant. There's different situations where you can change its speed relative to yours. That's relativity. Um, but there was no clear-cut answer on why light is locked in at that number, 300,000 kilometers a second. The reason, the the thought. So essentially, there is no answer. But the thought is that is a fundamental law of the universe in that because light is energy and light is a wave, it needs to propagate. And to propagate, it has to have a speed. So if it had an infinite speed, then it would no longer be a wave. So it's probably as much energy that can be used in that field, electromagnetic field, in a certain amount of space. It's pretty complex. It was mind-boggling yesterday. But in short, there's no answer. Roundabout, they're still researching it. Azra says she's in charge. Oh, boy. It almost fuels its own speed. It's fuels its own speed. The universe determines its speed. And it is part of the universe. So it's the universe kind of limiting itself, if you want to think of it that way. Because if the speed was not a constant, then you would have everything happening instantaneously. You wouldn't really have a universe at all. So it needs to have a lag period. Kind of think about the universe as a buffer. All right. So you've hopefully answered your DNA. I'll go over it. Some of you already took guesses on the first one. Hopefully it's not very hard. These numbers look really, really big. As big as 1,000. Something like that. So you would have to look at these large, large numbers and realize that you can make them smaller and it's easier to work with. So how about I jump over to the whiteboard. Let me ditch the agenda. So first we'll start with Ceres. Ceres is in the asteroid belt. Its mass is, was that 900 quintillion? Thousand, million, billion, trillion. Okay. So I think Rainey said there was 20 zeros. So 900 quintillion kilograms. I'll plug this into a calculator. It's going to be near impossible to use. There's too many zeros. So what do scientists do when they have to use mass? Like, let's say you want to find the density of Ceres. You got to do mass divided by volume. Those are huge numbers. But if you put it in scientific notation, you can make a small decimal and use two small decimals to find the density, but keeping it all in the power of 10. Because every time you multiply something by 10, you add a 0. So there's 20 zeros here. So you'd have to multiply 10 times itself 20 times. Because every time you multiply by 10, you add a 0, right? So you count up how many decimal places it would take to make this a 1 integer decimal. All right, so I'm going to go here. The decimal point's here, right? This would really be 900 quintillion 0.0 kilograms. So there's always a decimal point with a whole number. Just 0.0. We drop the 0.0 if it's 0.0. I'm going to move this decimal place over to make this 9.0. So 9. Okay? So I'm going to move it over and count how many times it takes. That's going to be my exponent times 10. Right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I'm moving this decimal point over to the left. Took 20 times. So now, a better way to write this, 9.0, because that's what I got right there. Decimal point's here now, right? 9.0 times 10 to the 20 kilograms. So the mass of Ceres could be right as 9.0, or just 9 times 10 to the 20 kilograms, because there's 20 zeros. Or I moved the decimal place 20 times to the left. Morning, Ryan. So that's Ceres. That's taking a standard number and putting it into scientific notation. Can you take a scientific notation and put it into standard is the next question. So kind of divide this into two parts, right? Pluto, famous ninth planet, discovered in the early 1900s, and then a little less than 100 years later, demoted to a dwarf planet. The definition of a planet was made the same time Pluto was demoted. So the definition was made in part to address the question of Pluto and the other objects that are in this Kuiper belt. Because as our technology got better, we were starting to find other objects in similar size, similar mass to Pluto. Eris, Makemake, Himeameia, Sedna, those are all Kuiper belt objects, or trans-Neptunian objects, TNOs. They kind of sometimes go inside the orbit of Neptune, outside the orbit of Neptune, exist around outside the Sun, outside Neptune, in a belt similar to where all the asteroids are. But they're much larger and more spherical than asteroids. So there had to be a new definition because scientists were wondering, well, these objects are all in the same kind of general orbit, whereas the planets that we know in the outer solar system, the gas planets, and the inner terrestrial planets, they seem to have, space between each other, and they don't really interfere with each other all that much. So they came up with that third criteria of a planet needs to clear the orbit around itself. Essentially, the IAU didn't want to make Pluto, keep it as a planet, because if it made Pluto a planet, then the other objects would have to be called planets. And so you would start adding tens to hundreds of planets around the sun. Ceres would become a planet. So the IAU wanted to keep it at 8. The 4 inner planets, the 4 gas planets. So that definition is a little bit of a very rare time where scientists start to get political with each other, and for certain reasons, certain classification. Pluto doesn't care if it's called a planet or a dwarf planet, but humans had attachment to it. So it was very interesting how that definition came about. And somebody emailed me yesterday about, can I use Saturn because it's got large rings and it's near the asteroid belt? And so does it really clear its orbit? So now you kind of understand why the definition isn't very good. All right, so we'll talk a little about that definition, and then if we were in the classroom, we would have had a debate, like I've done in the past, of do we want to change this definition or do we want to keep it the same? And those of you that change the definition, if you guys end up kind of winning the debate, some interesting things happen. Like you may demote some planets and promote others. All right, but back to that side, Pluto, its diameter got to double check, in scientific notation is 2.4 times 10 to the third kilometers. Morning, Troy. Guys just joined. We're going over the DNA, second part. You guys can watch back later today, see the first part. Diameter, 2.4 times 10 to the third kilometers. This is in scientific notation, but I want to put it into standard notation, right? So again, the way I worked before, as I move the decimal place over to the left, I'm going to move it over to the right. So I'm really multiplying 2.4 times 10 times 10 times 10. So I'm adding 3 zeros to it. Well, I'm moving the decimal place over 3 times. Okay, so I'm really adding 2 zeros, as you're going to find out. And Jake, you're kind of already ahead of me, all right, which is good. So the diameter, we're going to move that decimal place over 3 times to the right. So in the first one, we moved the decimal place over 20 times until we got to that 9. We're going to move this over 3 times. So 1, 2, 3. Decimal point goes there. We add zeros in the blank spot. All right. Maybe I rewrite this so it doesn't look messy. One, 2, 3. Decimal point there. Fill in any of the blank spots with zeros. And this power of 10 is gone. And there's your new number. So the diameter of Pluto, when you write it in standard format, is really 2,400 kilometers, which is not very big. All right. So remember, this is scientific notation. I'm sorry. Oops. This is scientific notation here. This is standard. So for series, we went from standard to scientific notation. Here, we went from scientific notation to standard. So in converting standard to scientific notation, move the decimal place over to the left, right in back of the first digit, so that 9. All right, we moved 20 times to the left, so we made it 9 times 10 to the 20. Okay, this is all powers of 10, because every time you multiply something by 10, you add a 0. Okay, even multiply by itself. For the diameter of Pluto, we did notation to standard, and in doing so, we move the decimal place over to the right. Okay, because we're multiplying it by 10 times 10 times 10. So you multiply 2.4 times 1,000. You get 2,400. All right. So there's other things you can do with scientific notation. This is the macro side of scientific notation, which means big numbers, macro. There is micro, which you probably do a little more in math, and that is going on a small scale. So we use this macro side of scientific notation for large objects like the solar system, whereas we use the micro side for talking about maybe bacteria, viruses, things like that, incredibly small, because you can work opposite. So for example, you could, you don't have to write this down, you could have 9 times 10 to the negative 3. Well, what does that mean? That means you got to move 3 spaces to the left. The decimal place is here, 1, 2, 3. Decimals here. Put this into standard format, you get 0.009. That would be 9,000th. So notice how 1,000 is positive, 1,000th would be negative. So negative is going into a small decimal. whereas positive, you're making a larger number. Macro, large, versus micro, small. What if all the gas giants collided? That's an interesting question. Maybe I'll look into that one, Hayden. Maybe that could be the next Ask Mr. G. Because would you have enough mass in the resulting object to finally conduct fusion at the core? Because Jupiter, sometimes called a failed star, it's kind of on that border between what we call a brown dwarf and a star. Brown dwarfs are in between planets and stars in that they're large, incredibly large, but they don't have enough mass and enough gravitational force to start fusion at the core. If you get fusion to happen, you get a star. No fusion, no star. So that'd be interesting to look up. All right, so that was the DNA. I really wanted to go in depth on that one, give you time to work on it yourself too, because it's going to be important. Because looking at large numbers, you're going to find these large numbers when you are conducting your research for tour of the solar system, especially when you are looking here. Distance from the sun, Earth is 150 million kilometers. I could write that as 1.5 times 10 to the trillion is 9. No, trillion is 12. Billion is 9, million is 6. So I could put that as 1.5 times 10 to the 6 kilometers. Okay. Mass and surface gravity, that is already reported to you in scientific notation. So I talk a little bit about scientific notation because you're going to find these numbers that are massive. All right, very, very large, times 10 to the 24, which is 4 magnitude larger in the series, which doesn't sound big, but that's an exponent. Remember, that's 10 times itself, right? This isn't multiplication. And so these will be relatively similar in standard notation, but these two are going to be very, very large, depending on your planet too, right? You start going to the outer solar system with the gas giants, you're going to get incredibly large numbers. All right. This surface gravity, what that means, 9.81 meters per second squared. That is not scientific notation. That is the acceleration of an object due to gravity. So, if you drop something, it speeds up 9.81 meters per second every single second. So it falls faster and faster every second. Okay. So we are doing research, right? I want to quickly just talk about this before we talk about the planets and what you're doing. Tour of the solar system. This is the rubric. Mr. G, how do I find the rubric? Under classwork, under tour of the solar system, right here. Rubric, 6 criteria, 24 points. You click it, the rubric pops up. Okay, but I already got it over here. There are 3 concepts, 3 research categories. The first 3, okay, right there. Geology and meteorology. Geology and meteorology, they match up with surface condition, specific landmarks or features, interior of the planet, and atmosphere, temperature, and weather. So these 4 boxes right here are going to be, I'm going to be grading on how much detail and how much information you provide for geology/meteorology, the weather and the formation of the planet. And geology, geo means Earth, so probably call it like exogeology, outside the Earth geology. All right. So exogeology, exometeorology, so for these other planets. All right. Astronomical phenomenon. So we talked about astronomy already. Sun, Earth, and Moon, rotation, revolution. That's incorporated into the table as well. Mass and surface gravity, mass, it's all going to play a role. Distance from the sun, rotation, revolution, these 4 are in the next category. Okay, so size, mass and surface gravity kind of correlate with size. The more mass, the bigger the object usually is. Distance from the sun plays a role in revolution, how long a year would be for that planet. Not for an Earth year, but for that planet's year, even though we're going to probably use it in Earth years. All right, rotational period, again, has a correlation with mass. The larger the planet, usually you're going to find out the shorter the rotation because the more momentum that planet has as it spins. All right, more energy. So that's all dealing with astronomical phenomenon. It's like Sun, Earth, Moon, except we're talking now Mercury, Moon, Mercury and Sun, or uh, Saturn and the Sun. All right, no Earth, no Moon. There are comparisons for the Earth that I put in there for you to use. Okay. The next category is miscellaneous research. So I just put in some things that you could use, like moons and rings and missions. So keep clicking on the whiteboard. Missions up here. I probably should have put it down here, but missions, moons, and rings. Is there a ring system? Are there any moons? There's only 2 planets without moons. Okay. What missions are to the planet? Some planets have a lot more missions than others. I would use the first initial missions to that planet and then any in the last 5 to 15 years. Okay, the recent ones and the early ones. The early ones kind of set the stage for what we use now. Okay, so there's a lot of information. Some planets can have more information than others. Like again, yesterday somebody asked, Mr. G, what do I do for surface conditions of the gas giant? I told them to talk about the appearance. Why is the appearance the way it is? Jupiter, Saturn, Uranus, and Neptune all have a unique color about them. Jupiter is more brown, red, gold. Saturn seems to be a yellowed or gray. Uranus is greenish to bluish. Neptune is bluish. Why do they each have their own colors if they're all pretty much made out of hydrogen or helium? So that's pretty interesting in terms of the color. So the appearance from outer space is something I would maybe include with surface conditions, even though that kind of gets into the atmosphere composition. So just be careful. There's more things you include for others, all right? But something like Mars or something like Venus, places where there is a solid surface, Mercury, yes, you include a lot of information in that. Specific landmarks. Are there mountains? Are there valleys? Are there canyons? Is there things that have names that you can include? That's what I would include there. All right, so I'm just kind of thinking of some questions people had yesterday. Missions I addressed, surface conditions, landmarks. The interior of the planet, we haven't talked much about the interior, but the Earth has a crust, a mantle where convection occurs that moves the surface of the Earth. And then it has a liquid outer core and a solid inner core. I actually flipped these. And so just kind of see if there are layers to your planet compared to the Earth. All right. Atmosphere, temperature, and weather. Again, that should be pretty readily available. Rotation period, revolution, that should be readily available. Moons, some planets got 60, 70, 80 moons. Some planets got 2. Some planets have 1 or 0. So some planets have more information than others. And the same thing with the ring system. All right. So again, when you have questions throughout the day or now, I see a couple in chat. I'll address them in a second. If you have questions, ask them, and I'll clarify as best I can. All right. Yesterday, hopefully you did like 2 or 3. You did like the first 3. I would do the next 3 today. So I would do, if you did the first 3 yesterday, I would do interior, atmosphere, and distance from the sun. All right. Because Jack's asking me, when does all the research have to be done? This document is not due until next week because you're going to put slides in here. All right. That will be next week. I want your research hopefully done this week, over the weekend, ready for Monday. So have your research ready hopefully for next Monday. Okay? If you got to do a little more, you got to do a little more. All right? I don't get what we're supposed to write for missions for the planet. I didn't watch the live stream from yesterday. Well, you know what your best thing to do is then? Is to watch the live stream from yesterday, right? Every day, if you guys haven't noticed, I make a comment, I post the stream, and I give a timestamp for different stuff. DNA number one's at minute 11. Introduction to Tour of the Solar System. So, Sammy, I would go to the stream, I would go to minute 30, and I'd just listen, pay attention to what we were talking about, all right? And you get an intro to what we're doing, okay? And like yesterday, I also said I would provide some examples of accurate, reliable sources. Solalsystem.nasa.gov, perfect. natgeo.com/space/our solar system has some good information. Earthsky.org is more for exploring astronomy, but there is a space category. I mean, this one's talking about exoplanets. This one's talking about Pluto. This one's talking about Mercury. So if you're doing Mercury, first man in space, they're talking about Yuri Gagarin. Mercury again. A comet. Was Mercury once habitable? Dark energy. Hike, if you're interested. That's why the expansion of the universe is faster than the speed of light. 100 new minor planets beyond Neptune. 100 new minor/dwarf planets. Told you that the IAU wanted to make a certain definition. So there's some things you could find on this site, a little better than space.com. I don't like space.com. It's full of ads. It tracks you what you're doing online. Some information is good on there, but earthsky.org is better. All right. So some sources are there for you to use. You want a refresher, go back to the live stream from yesterday, look at the timestamp, go to minute 30, get a review of what we were talking about yesterday. All right. Or ask questions right now, like a couple of you are doing. Okay. So what we're supposed to write for the missions of the planet, kind of address that again. Give me what were the first couple of missions to your planet of choice. All right. So for example, if you're doing Mars, the first missions that were really there to study the surface conditions of Mars were the Viking missions for NASA in the 70s. So you would be searching for missions to Mars. You come across Viking. I would put Viking on there. Viking's goal was to see if there was microbial life on the surface of Mars. All right. And then later on, in the last decade or two, we've sent Spirit and Opportunity rovers on the surface of the planet to examine if there was liquid water in previous eons of Mars' geological past. All right. We've had the Mars Reconnaissance Orbiter looking for possibility of life, water under the surface. The InSight lander landed a couple of years ago. Its goal was to send a probe into the Martian crust, if you want to call it that, and to monitor for Mars quakes, which it picks up to see if Mars is geologically active. Because if it's geologically active, we can start to get an idea of why Mars lost its magnetic field at one point, and maybe that's why it lost all of its water on the surface. So there's different missions there that kind of provide the surface conditions and what kind of happened to the planet. All right. If you're doing the outer planets, Jupiter, Saturn, Uranus, and Neptune, the first missions to these planets were looking at, the big ones. I talked yesterday with the Voyagers 1 and 2. They completed the tour of the original tour of the solar system. All right. They looked at these outer planets for the first time instead of just a telescope from Earth. All right. And so the Voyagers in the 70s and 80s, they snapped the first pictures up close of these gas planets, took the first measurements. Jupiter had the Galileo probe, Galileo orbiter sent to Jupiter. The Cassini probe was sent to Saturn. Huygens was sent to one of Saturn's moons, Titan. Uranus and Neptune, again, they had the Voyagers. I'm not up to date on whether there was any recent ones. I don't think New Horizons took any pictures of them. All right, but there's other missions that you could include. Recent missions in the last couple decades, last 5-10 years, and then the initial ones. All right, Voyagers are the big ones. Pioneer, Voyager, Pioneer, Viking, those are the big early missions that we started using to explore our solar system. All right. So missions help lay the groundwork for everything else. The reason why we have this information is because of this first column, which is probably why I put that column there instead of down here with moons and rings, because that's part of miscellaneous. I wanted you to see that these right here led the groundwork for the rest of this. Okay. When do we start the presentation or the slides? So you need the groundwork, right? You need notes, you need information. Once this is done, which my goal for you is hopefully next Monday, once this research is set, you start making slides on Monday. You finish making them Tuesday or Wednesday, you start recording yourself with Screencastify. It's an extension you add to Chrome, and what it does is it helps you record your screen, but it can pick up your mic. And so you guys can narrate your slides. So Monday, Tuesday, maybe into Wednesday, you guys are working on slides and then recording them. And then it uploads, or it should upload to your drive, and then you just put that link in here. And then I can watch your presentation. All right. Any other questions? Again, if you haven't used this source, I would definitely use it. Solalsystem.nasa.gov gives you a good overview of each of the planets. And if no one's got questions, maybe I'll just go over each of the planet in brief, things to find, to look at. Already has right here some basic information that you could use. Mercury is the smallest planet in our solar system, closest to the sun. It's only slightly larger than Earth's moon, so it's about on the same size as the moon. Yet the moon's a moon and Mercury's a planet. Big difference. It's only slightly larger than Earth's moon. Mercury is the fastest planet zipping around the sun in only 88 Earth days. So 1 year on Mercury is 88 Earth days. Okay, ours is 365 and a quarter. An AU, if you don't already know, that means astronomical unit. What is an astronomical unit? It is the distance from the sun to the Earth. So it's 0.4 AU. It's about half the distance of the sun to the Earth. So if 1 AU, if I told you before, it's about 1.5 times 10 to the 6 kilometers, 150 million kilometers, then you're probably looking at half that. You're probably looking at about 70 million kilometers, because it's not exactly half. All right, but actually look up to see what the actual distance is. You can Google that and find a source for that. See, AU, astronomical unit, distance between the Earth and the Sun. It's kind of like, we have an AMU when we talk atoms, right? A proton and a neutron are 1 AMU. AMU, atomic mass unit. So we just give a distance. It's an actual number, but we just give that as 1. So we set it as an arbitrary unit, a human-made unit, right? There's an actual mass you can give a proton, but we just use 1 AMU for simplicity, especially in middle school. And you can read more about Mercury, okay? Venus. Venus spins slowly in the opposite direction of for most planets. So this one's the outlier. You're doing Venus, pretty weird planet. In that, a day on Venus, that's not here, is longer than its year. Spins slowly in the opposite direction. So instead of everything going counterclockwise, Venus is rotating clockwise. Very interesting. 0.7 AU, 225 Earth days to complete a year. Click read more, you can find more information. I really want to know how long its revolution is. I can't believe it's not showing it. Yep, day longer than a year. One day on Venus lasts 243 Earth days because Venus spins clockwise backwards. All right, very interesting on why that's happening. You might think, well, it was due to a collision. Well, if something that to make it turn the opposite rotation, the amount of energy needed would be an object so large it'd probably destroy the planet. So it probably isn't from a collision. We're skipping Earth, right? Because we talk about Earth a lot already. I can't zoom out. There we go. Mars. Dusty, cold desert world with a very thin atmosphere. Strong evidence Mars was, billions of years ago, wetter and warmer with a thicker atmosphere. So was life possible in Mars, on Mars, billions of years ago? It's almost double on Earth here, because it's 1.5 AU. It's got 2 moons. You can read more, find more information. And then you kind of go past these inner planets, and you are now in the asteroid belt. Okay, we're talking millions, billions of objects. They vary from the size of, a computer to we're talking the size of a dwarf planet. Ceres, Eros, Psyche, Vesta. Vesta is the second largest asteroid. Ceres is the largest of the asteroids, but it is classified as, because it's in other space, a dwarf planet. Ceres makes up almost a third of the asteroid belt's total mass, but is still far smaller than Earth's moon. Ceres is heavily created with large amounts of ice and underground, but impacts with other asteroids and meteorites show this ice on the surface, and there's bright spots on Ceres, which we think is this ice. Okay, so it's in the asteroid belt, and this is kind of where the definition comes into play to make something a dwarf planet. Okay, the first criteria, it's got to orbit the sun. Well, Ceres orbits the sun. So does the Earth, Venus, Mars, Mercury. Okay? Well, now in the second part, it's got to be spherical under its own gravity. Well, all these so far we looked at are spherical. Is everything spherical? Eros is more of like a little potato. Psyche is pockmarked and also looks a little bit like a potato. Vesta's a little more spherical, but still, it's not completely a sphere. It's not a ball. All right, and they got its name as a protoplanet. Like if you give it enough time, enough mass, it may form a planet. Except there's a large planet that kind of prevents that from happening. So most asteroids are a little oblong. They're potato-shaped. They're made of different elements and compounds: carbon, iron, silicate, things like that. A lot of ice. Ceres is spherical shape. So you got to be a sphere. These aren't spheres. Bennu, not a sphere. Looks like a football. Okay. So now the question is, does it clear its own neighborhood? There's objects around it, but is it the most dominant source of gravity in that area? For Mars, Earth, Venus, Mercury, sure, Earth and Mars have moons. Venus doesn't really have anything else in its orbit. Okay, but here's the problem: these asteroids cross orbits. So the gray area is, do objects really clear their neighborhood if there's other objects near them? So Ceres, Eros, Psyche, and Vesta, even though Ceres is so much larger, they consider a dwarf planet because it's in this same orbital plane as the asteroids. And so I'm not a big fan of the definition. But at the same time, I don't know what else to propose at this moment. What would you make a planet? I think there's some interesting things you could use, but I don't know if my idea is any better than anybody else's. So, Ceres is a dwarf planet because it's in this asteroid region, even though asteroids cross the inner solar system all the time. So, why is Venus a planet when Bennu's kind of crossing its orbit right now? Or even entering Earth's orbit on the other side of the sun? Go a little further out into the outer solar system. Jupiter is the big reason why these do not form into planets, because Jupiter's gravity is constantly pushing and pulling these asteroids around the sun. There's something called the Greek asteroids and the Trojan asteroids, the little bundles of asteroids before and after Jupiter. There's some good gifs online. There we go. Greek and Trojan asteroids. Yeah, just like the Trojan War. Opposing groups of asteroids. A little connection to Mr. Howman's class. Jupiter keeps these at Lagrange points where gravity between these points are equal, and so it prevents these objects from ever forming a planet. If Jupiter wasn't there, maybe you'd have a planet. But if Jupiter wasn't there, you wouldn't have a large planet deflecting comets and asteroids away from the Earth too. All right. Jupiter's year is 11, almost 12 Earth years, 5.2 AU, 5 times further out. Great red spot, big surface feature. Saturn, obviously, it's got its rings. It takes 29 years to orbit the sun. All right. The distance from the sun to Jupiter is about half that of Saturn. So in the outer planets, the distance starts almost doubling. So sun to Jupiter, the distance from the sun to Saturn is double the distance from sun to Jupiter, roughly. All right. 62 moons. Jupiter, 79. Planet 7, lots of pronunciations. 84 Earth years, almost 20 AU, 27 moons. Has that 90-degree tilt. And then you have Neptune. 165 Earth years to do one revolution around the sun. It is 30 times further from the sun is to the Earth. 8th and most distant major planet orbiting our sun, dark, cold, and whipped by supersonic winds. So far away from the sun, how does it have supersonic wind? Don't we need solar energy? Very interesting why that might happen. See if you can find that out. 14 moons. Uranus has 27. Past Neptune, like I said before, there's almost like another belt. Except that some of these objects are a little larger. Some of them are smaller. It's like the asteroid belt to begin with. There's more dwarf planets. The most famous, Pluto. 249 years to go around the sun. 39 times further than the Earth is from the sun. It has 5 moons. So it does have moons. And then you have the other dwarf planets. Hawaiian gods and goddesses, Makemake, Himeaumea. Eris is out there. I don't know where Eris is in this image. And so is Sedna. Those are other famous. There's Eris. Other famous dwarf planets. Don't even have a direct image of it. Well, we do have a direct image, but not very close up. We have Pluto's image because of New Horizons. This probe right here. One of 5 spacecraft that will eventually leave our solar system. It did do a flyby of a Kuiper Belt object, Ultima Thule, which looks like 2 potatoes put together. And then you keep zooming out, and eventually, it's not here, but we'll take a look at it soon. There's something around the Kuiper Belt called the Oort cloud, and that's kind of where a lot of these comets come from, like Hale-Bopp. Takes 2,534 years to reach the sun, to make one orbit a very elongated elliptical orbit into the sun, into the interior solar system. So it last came in 1997. You're not going to be around to see it again. Okay, that is in the Oort cloud, about a light year away from the sun. Very far away, but it is considered a kind of like a reservoir of all the comets that we think of. Troy, what would happen if Jupiter went 10 miles per hour faster? Would that throw off the way weather works there? So you got to be a little more specific on went 10 miles per hour faster. Do you mean the rotation or do you mean its revolution? If you mean rotation, then I would say, yeah, because you would have a stronger Coriolis effect. You would have things curving more to the poles on Jupiter, right? So if it rotates faster, you have a stronger Coriolis effect. However, Jupiter has the shortest rotation period already out of all the planets because it's so large. So if you're making it go faster, you're probably adding mass to it, which would make its gravity stronger, which means it holds on to more gas, which means it is going to have more material to conduct energy with. So yeah, you probably have more severe weather. Something more than you have now, probably not a lot more severe, but you'd still have the Great Red Spot and large storms. Okay? Revolution, again, deals with distance. Slower revolutions are further from the sun. So you'd have to be moving further from the sun, which means less sunlight, which means less energy for weather. So if we're increasing the revolution speed, we're probably moving closer to the sun, which again means we're gaining more energy. So yeah, if it moves faster, indirectly we're going to have more severe weather, more energy for the weather. Yeah, the rotation. Yeah. Stronger Coriolis effect. Remember the Coriolis effect? Can't travel in a straight line over a rotating object. It's got to turn in a curve. There you go. Downey, I don't understand what we are supposed to write down in the box of the interior of the planets. So, because we're not doing Pluto, let's see if there is an interior of the Pluto. They have any information on it. Small in size, small world, slow journey, hazy days, soul encounter, harsh habitats. Does not look like there's an interior. So now we gotta take it to Google, right? Interior of Pluto. Do a little bit of research. See, now there's some cutouts. We can see what's inside to the middle of Pluto. But we got to make sure this is an accurate, reliable source. So, Forbes, that could be useful. Pluto in depth, maybe I missed something right there. Space.com. Rochester.edu. These are images of the Hubble Space Telescope, not very in depth. Nah, not good. Too old. Size and distance, or rotation structure. Pluto is about 2/3 the diameter of Earth's moon, probably has a rocky core surrounded by a mantle of water ice. Interesting ices like methane and nitrogen frost coat its surface. Due to its lower density, Pluto's mass is about 1/6 that of Earth's moon. So we have a crust with ice, like methane and nitrogen, and then we have a mantle of water ice with a rocky core. So we have a core, a mantle, and a crust. How do I know that? I went to solarstym.nasa.gov. I pasted it into this box. If I haven't already used it for these three, paste it in, and then I tell the layers, maybe tell me what it's made out of. All right? Or have you note what it's made out of. But there's other sources you could pull, not just that. Like this is .org, so technically it should be accurate, reliable. Just, I don't know about the name, Windows to Universe.org. Keep in mind you guys aren't doing Pluto. I'm just using this as an example. If it would load, we could actually take a look at it. There we go. Yeah, alright, it's an org. Ice Mantle 1, Ice Mantle 2, core. Images from NASA. Okay, but it doesn't tell me what it's made out of. Composition is mostly ice. Well, what type of ice? We know it's nitrogen and methane because of NASA. Enough energy for turning over of the layers inside of Pluto. Oh, that was what was on space.com. Ripples on Pluto's subsurface ocean. So that's interesting. I don't know how you get a subsurface ocean if there's nothing big there to cause friction. Heat. But yeah, that's how you would start getting the information, put it in. All right. What layers does it have? Maybe what is simply what's in them. All right. Hayden, inside of it's made of like the mantle and the core. Yeah, that's. Yep. You're trying to help out Downey. That's good. Yep. Bergeron, can we copy and paste information? Yes, but I would bullet information on your slides, and I would put your explanation when you record it or when you write it in your own words. Yep, you got to give them credit. You put the link in your research, but also the link to get a 4 on your slides, 4 out of 4. Sources are per slide, or you make like a small works cited. You put them in alphabetical order at the end, like the last slide. Your sources, link me your sources. Okay. Incorporation of sources per slide or at the end. So yeah. So in addition to your table, make sure it's in your slides later. But explanations are in your own words. I don't want to hear you narrate an article that I could just read. All right. I don't have any questions on email. I don't have anything on Remind. Do you guys have any other questions? Why is there salt there? For my other boxes, I use NASA for each one, but they were different sections, so there's a different link. Can I use NASA for the other boxes? Technically, yeah. Well, is it still? You're good, Troy? Good. If it starts with solarSystem.nasa.gov, please try to use something else. I want you guys to be able to look at multiple sources. I don't want you just being able to pull right from this website. It's a great website. It's got all the information you probably need, but I want you to branch out too. So you know what I would do is I would use this website and this source for the harder ones to find. And the harder ones to find are probably interior of the planet, surface conditions. The rest, you can find these easy. This is all standard information. The astronomical information is all standard. Okay? A lot of this information right here, geology, meteorology, comes from the missions that NASA did. So NASA has the best information. So I would kind of maybe use NASA for this section and other sources for astronomy. Hopefully that helps you out a little bit. I don't want you to... If it says this, see how in a URL there's like a white part of a URL and there's a gray part? This is the main website. This is the source, not the gray part. Okay? Hike's letting me know Screencastify has a 5-minute limit. Really? Not aware of that. If we want to do a part 1 and a part 2, you can do that. If you can crunch it down to 5, that's even better. I'll talk to Mr. Hellman about that, because he's the one that uses Screencastify a lot. For my YouTube videos and streams, I'm using OBS. He's using OBS now too, but he used a lot of Screencastify in the beginning. I'll ask him about that. Thanks for bringing it to my attention. Jake, I'm just confused on how I am supposed to list the core of Neptune. Well, what source are you using? Oh, let's find Neptune. The windiest planet, yet it's the furthest away from the sun. In depth. So it tells you what's inside the planet, Jake. I'm not sure how I'm supposed to list the core of Neptune. The core is just one part. You would list each of the layers and tell me what they're made out of. I mean, it's obviously got an atmosphere, so I don't know what it's talking about there. Maybe this isn't the best source, but there is an atmosphere. Most of its mass is crushed down due to its dense gravity. Due to gravity making it denser, so it's more of like a liquid, hot liquid, or hot ices. Ice because ice is a solid. So the density of the planets, the gravity of the planets crush things down to a solid. All right. And then a small rocky core. Neptune is the densest of the gas giants. So I would do core, and then you'd have to give it a name. I would maybe say that it would be a maybe call that like a mantle, or call that an outer core of icy materials. And then obviously its atmosphere. Primarily what? Methane, helium. This doesn't have a lot of information on the different layers. Maybe try another source. All right. So if you have questions throughout the day, let me know. I'll answer as best I can to help guide you along. I think everybody else is good. Miss Grant's starting up. Miss Kildoff's taking you guys with her. Let me know if you got questions. All right. See you later. Bye, Ezra. See you, Rainey. Bye, Ron. Bye, Downey. See you, Charlie. See you, Hike. Bye, Eric. You too, Troy. Thank you.